Hello guys, welcome to plcgoods video tutorial. In this video, I will have a short review. Then I will explain the bit logic instruction briefly in RSLogix 5000. Also, I will do a project to sort boxes based on their height in Factory IO. Until now, we learned to work with RSLogix 500. With this software, we can configure and program some Allen-Bradley controllers like MicroLogix and SLC 500 series. Also, we use RSLogix Emulate 500 to test our programs without any real controller. Then I explained how RSLogix 5000 can be connected to a real PLC via its serial port or an Ethernet module. This software supports some Allen-Bradley controllers like ControlLogix and CompactLogix series. After that, I introduced Factory IO that we can use it to simulate some industrial processes. In the previous video, I designed an HMI screen using Factory Talk View to monitor and control my PLC program. From now on, I prefer to use PLC Trainer controller and Factory IO to test short programs. We already learned how to configure a PLC station in RSLogix 5000 and to generate some simple programs and test them with a real or virtual PLC. Here are all the instructions that we can use them. These instructions are divided into several categories. In this video, I am going to give you a brief introduction to bit instruction sets and after that to define and do a simple project with Factory IO. Let's start with these three instructions: examine on, examine off, and output energize. When I press the start push button, an AC or DC voltage reaches my PLC input terminal, and if I use its address for this examine on instruction, PLC closes this contact in my program. In consequence, the virtual power can reach the output energize instruction. So if I connect output 1 address to a digital output of my PLC, it can turn this lamp on. But examine off instruction works inversely. Now in normal conditions, this normally closed contact passes the virtual power in my program. Therefore, my PLC turns on the lamp in normal conditions. If I press the push button, the electrical power reaches the selected input of the PLC. In consequence, my PLC opens this contact to break the virtual power path and the lamp is turned off. Note that a PLC first scans all its inputs to determine if any of them is activated or not, and it saves all this state information in a data table. Then it executes the whole program from the first run to the last one. Then it updates its outputs. After that, it does some tasks like checking communication requests and housekeeping. Then it restarts the scan cycle. Now let's see what latch and unlatch instructions are and how we can use them. I explained the output energize instruction already. In the first run, based on the state of input contact, the output 1 will be on or off. In the second run, the output latch instruction can only set output 2 to 1. Note that if I enable output 2 with the output latch instruction and disable it, the input contact will still remain on. The last unlatch instruction works inversely. It can only reset bit addresses to 0. Note that here I have used both latch and unlatch instructions for the output 2 tag. If I enable this contact to enable both instructions, the unlatch instruction has priority over the latch instruction. Because I have used the unlatch instruction, after the latch instruction. Now let's see what the one-shot instruction is. This instruction can activate a bit of memory or an output during one scan cycle. For instance, when we enable this contact, the current program executes the add function only once. Note that it does not matter if enable bit is closed or open. Due to the one-shot instruction, only the moment of activation is important. The one-shot rising instruction works similarly, but it needs a bit of memory to work correctly, like the one-shot instruction, but it also needs another bit of memory as its output. We can use that in another run our programs. Similarly, we can use one-shot fouling instruction. In the current program, its output address will be on only for one scan cycle when the state of this contact changes from 1 to 0. Let's define a project to learn the bit instructions. I want to write a program to sort boxes based on their height. I will use the PLC and Factory IO. Obviously, this project includes a belt conveyor, a control box, and a pusher. From here, Factory IO places boxes on the belt conveyor automatically. Then it moves all the boxes. Here is a sensor that detects large boxes. The belt conveyor moves all boxes to its right side, but the bigger boxes should be pushed by this pusher on this chute conveyor. First, let's design the sorting box plant in Factory IO with this system which was explained already. Now let's insert an emitter from the right list. For changing the height of an object, I press the V key and use the mouse to change its height. Now let's right-click to unmark some items to just keep a small and large boxes. Now let me move this control box a little. Now from the right list I need to insert a pusher. I can use this pusher to push boxes, which it includes two sensors. If the pusher is not extracted, its back limit sensor is set to 1 and its front limit sensor is set to 1 when it is completely extracted. So these sensors determine whether the pusher's arm is extracted 100% or not. Now let's insert a diffuse sensor. When a large box with enough height appears in front of this sensor, it sends a signal to a PLC, so I can use this sensor to detect large boxes. Now I want to insert two chute conveyors. Now let's insert two removers at the end of each chute conveyor. I finished inserting my equipment in Factory IO. Now let's start the programming steps. Let's start with this program which I explained before. We have used this program to turn on and off a belt conveyor with two real and two virtual push buttons in Factory IO. Now let's write a program to turn on and off the belt conveyor using the latch and unlatch instructions. I will use the first run of my program to activate this output with a real input and a virtual input from Factory IO. Now I press Ctrl plus D keys to modify the description of the selected output address. Similarly, let's use an unlatch instruction to turn off the belt conveyor. In the next run, I use another latch instruction to turn on the second output. I will connect this output to the pusher in Factory IO. The PLC should activate the pusher when this sensor detects a large box. So let's use a bit of the Factory IO tag for the inserted contact. I need to connect this tag to a sensor in Factory IO. Note that if a large box arrives here, the sensor will be activated, but the large box will not be in front of the pusher. Note that when the sensor's state changes from 1 to 0, the large box will be in front of the pusher and it can be pushed. So I need to use the one-shot fouling instruction in my program. This part of my program turns on the pusher when the diffuse sensor detects a large box and its state changes from 1 to 0. When the pusher is extracted 100%, its front limit sensor is set to 1. I can use that to turn off the pusher. Pay attention, until now I have used 4 bits of the Factory IO tag, Factory IO.0 to Factory IO.3. Now let's connect the inserted equipment in Factory IO to my controller. Based on my controller type, I should select Allen Bradley Logix 5000 item and click on Configuration. Here I write my Ethernet module IP address. I can read it from its LED display. Note that the slot number of my CPU module is 1. Here I need to enter the input-output addresses into the program. I have used the Factory IO tag in my program for the input devices like push buttons and sensors. So I write it here. Remember that I only used 4 bits of it in the program. Also, I have used my first and second output. Note that their addresses start with local 3.0 data. Now let me change this number to 2 and the next numbers to 0 because I have not used any integer or floating data in my program. Now let me connect Factory IO to my PLC using a LAN cable. Finally, I need to connect the equipment to my PLC program via the selected addresses. Let's download the program to my PLC. Before that, let me modify the type of this contact because its related push button in Factory IO is normally closed. Okay, I downloaded the program to my processor and the equipment in Factory IO is already connected to my controller. Now let's test the project. First, I have to change my controller mode to run mode. Obviously, I can use my real push buttons to start and stop the belt conveyor. I can use the start and stop push buttons in Factory IO as well. Now we are going to learn the timer instructions, which are timer on delay, timer off delay, retentive timer on, and the reset instruction to reset the timers. Also, we will use the timer instructions to improve the box sorting project. Here are the timer instructions. Let's start with an on delay timer. This timer is used when an application requires an action to happen at some time after the run conditions for the timer becomes true. When we want to use a timer, we must create a related tag and enter its preset and accumulated values. The timer's name should be defined before entering the preset and the accumulated values. So let's right click on the timer's name and select new. Here I can change the properties of the tag. Note that I need to use timer as the data type of my new tag. Here I can select where the new tag should be created. Let's use the default properties. I created the new tag. Here I can see the structure of my new tag whose data type is timer. It includes some status bits and two numbers. The first parameter is the preset value of the timer, which its data type is double integer. So this parameter uses 32 bits to store a desired time. Note that the time amount should be entered in milliseconds. The accumulated value shows the current time of the timer. The enable bit, whose data type is Boolean, indicates whether the timer instruction is enabled or not. The timer timing bit indicates if the timer is in timing mode or it is stopped. The done bit indicates if the accumulated value reaches the preset value or not. This diagram shows how an on-delay timer works in RSLogix 5000. When we enable a timer, PLC enables the enable timer timing bits and the timer starts its work. If the current time reaches the preset value, the done bit changes from 0 to 1. Note that the timer's time should be entered in milliseconds. For instance, 10 seconds is equivalent to 10,000 milliseconds. Let's enter 10,000 milliseconds as the preset value. Usually we don't need to change the accumulator value, but if we enter a different time value when the program is downloaded, this time is used for the first scan cycle. Note that if the timer is not enabled during the first scan cycle, the accumulator value is reset to 0. Let me use the inserted on delay timer to turn on an output after 10 seconds. Here I use the done bit of my timer to turn on the output after 10 seconds. Now let's verify the program. Here is an error. I forgot to create this tag. Let's verify the project again. Obviously there isn't any error, so let's download the program to a virtual processor. I need to change the virtual processor mode to program mode before downloading this program. Now let's select the run mode. Obviously, if I activate this contact, the output will be on after 10 seconds. Now let me show you another way to use this timer. First, instead of this contact, let me use a normally closed contact which is connected to the done bit of the timer. Now based on the first run of my program, the timer restarts after 10 seconds automatically. The accumulated value is equal to the current time of the timer. Its value is incrementing when the timer is in timing mode. This address, timer1 ACC, includes 32 bits to store the current time in milliseconds. I want to use one of them to turn on off the output with a fixed frequency. Let's download the program to see its performance. The timer is activated every 10 seconds automatically and I have a flasher contact. I can use that to have a flasher output at the second run. For instance, this flasher output can be used to simulate a flashing red or yellow light of a simple traffic light. Note that I used bit number 10 of the timer accumulator address. I can use another bit of this address to have a faster or a slower flasher light. Okay, let's see how a timer off delay and the retentive timer on work. We saw how an on-delay timer turn on an output after a delay. An off-delay timer works in contrast to an on-delay one. When we enable an off-delay timer, a PLC enables the done bit of this timer immediately, but on the other side, it turns off the done bit after a specific delay. A retentive timer on delay operates the same as an on delay timer, except that it keeps the last time which is stored by the accumulator word even if we disable the timer. For instance, in this diagram, at the next activation, the accumulator will start from 4 seconds and the timer only will need 6 seconds to reach the preset value. After that, the done bit remains on until we reset this timer with a reset instruction. Here is the reset instruction, which we can use it to reset timer and counter instructions. Now let's do a simple project using Factory IO. We did a box sorting project in the previous video. Now I want to improve its program by using timers. In this project, if I press the start push button, PLC should activate the siren alarm for the first 5 seconds. After that, it turns it off and activates the belt conveyor and this warning light. Also, if I press the stop push button, the belt conveyor should be stopped after 10 seconds to move all boxes. This is the PLC program that we wrote in the previous video. Also, I configured my hardware here under I/O configuration. Now let me insert an on delay timer and use its done bit to turn on the belt conveyor after 5 seconds. Similarly, let me insert an off delay timer and use its done bit to turn off the belt conveyor after 10 seconds. In another run, I want to use a contact of the belt conveyor to turn on the warning light when the belt conveyor is moving boxes. In this project, we need to add two new digital outputs. I will connect this digital output and the next one to the warning light and the siren in the Factory IO. Now, based on the last round, when the belt conveyor is on, the warning light will be on as well. Similarly, let me insert another round to turn on the warning siren. Here, let's connect this contact to the timer timing bit of the first timer because this bit will be on only during the first 5 seconds. Now let me compile and download the program to the controller. I also need to modify my design planned in Factory IO. I need an alarm, siren, and a warning light, which should be connected to these two addresses. We designed this planned in the previous video. Now let me insert a warning light and the siren from the right list. Now let's open the file menu and select drivers. Obviously here I should select my controller type. Here I should write my controller IP address. Here I specify the slot number of my CPU module. Also I need to determine the tags which are used in the PLC program that should be connected to the equipment in Factory IO. Let's keep these settings from the previous video. Now let me connect Factory IO to the controller. I only need to connect the warning light and the siren to these digital outputs of my controller. Okay, let's see how my PLC program is going to control this plant. First, I must change the controller mode to run mode. Based on my controller program, I need to press and hold the start push button for 5 seconds to start the belt conveyor. Now if I press the stop push button, the belt conveyor should be stopped after 10 seconds, but it stopped immediately. Probably there is a bug in the program. See this part of the program. When I press and release the stop push button, the timer done bit is on for 10 seconds and it turns off the belt conveyor immediately because I used an unlatch instruction. To resolve this problem, I can use a one-shot falling instruction to detect the moment when the done bit changes from 1 to 0 after 10 seconds. Now let's download and test the program. Now when I press the stop push button, the belt conveyor will be stopped after 10 seconds. Okay, counters are similar to the timer instruction, except that a counter accumulates the changes in the state of an external trigger signal, whereas timers increment using an internal clock. Now I will explain the counter instruction, which are count up, count down, and reset. Finally, I will use a count up instruction to count the boxes which are moved by a belt conveyor. Okay, I am using RSLogix Emulate 5000 to create this virtual PLC station and define its modules under I/O configuration submenu. The counters are generally triggered by a change in a Boolean address that causes false to true transition of the counter ladder run. It does not matter how long the counter is enabled or disabled, only the transition is counted. Here are two basic types of counters, count up and count down. Also, we can use the reset instruction to reset the accumulated value of counters to 0. Now let's insert a countdown instructions. First, the counter needs a tag of the type counter. Then I can fill its preset and the accum fields. I need a tag whose data type is counter. Let's create it under the main program. Now let's see the created tag in my program tags table. The created tag has several parameters. The first one is the preset value. If the counter's value is equal to or greater than the preset value, PLC enables its done bit. The accumulated value is an integer number. It changes based on the 0 to 1 transition in the counter ladder run. We can use a reset instruction to reset this value to 0. If we use a countup counter, the CU bit, the countup enable bit, indicates the countup counter is enabled. Similarly, for countdown counter, the CD bit indicates the countdown counter is enabled. The next status bit, whose name is done bit, will be 1 if the accumulated value is equal to or greater than the preset value. The overflow bit indicates the counter's value has exceeded its upper limit. The upper limit of the counter's value is plus 21, 47, 48, 36, 47. Similarly, the underflow bit or UN indicates that the counter's value has exceeded its lower limit value, which is equal to minus 21, 47, 48, 36, 48. This diagram shows how an up counter works. When I activate this contact, the enable bit of the counter will be activated too, and the accumulated value will be increased by 1 unit. This process will continue until the accumulated value reaches the preset value. When the accumulated value is equal to or greater than preset value, the done bit will be on. After this amount, I can continue to increase the accumulated value by activating the up counter. Also, I can use a reset instruction to reset the accumulated value to 0 whenever I want. Similarly, this diagram shows how a down counter works. Like the up counter diagram, when the accumulated value is equal to or greater than the preset value, the down bit will be 1. Pay attention, this counter works inversely. By each counter activating, the accumulated value will be decreased. When its value is reduced to less than the preset value, the down bit changes to 0. Let me complete a simple program to test a down counter. For this contact, let me use a digital input of my virtual PLC station. In the next round, I want to use the down bit of the counter to turn on a digital output. Finally, let me use another digital input to reset my counter. Now let me verify my project. Then I need to download the program to a virtual controller. PLC decreases the accumulated value by 1 unit per each counter activation. Now, by the next activation, the accumulated value is reduced to less than its preset value. So, PLC changes the done bit from 1 to 0. Also, based on the last run, I can use my second digital input to reset the accumulated value to 0. Okay, we did the sorting box project. Then we improved it with the timer instructions. Now, let's improve it further using a counter. I want to use a count up counter to count the moved boxes by the belt conveyor. So, let me insert another sensor to detect all boxes. Note that the next sensor detects only large boxes, but the new sensor detects passages of all boxes. Let me modify its name to sensor 2. Now I want to find and insert a digital display from the right list to display the number of all moved boxes. This is the name of the digital display. Now let's right click on it to select which data type we need to display. In this project, I need to select integer. Note that we can activate each equipment manually by selecting its forced mode. If we need to control it with a PLC, we should release it in Factory IO. Now let's modify the connection settings because I inserted a new sensor as a digital input and a digital display as an output to receive integer numbers. I don't need to change my controller IP address and its slot number, but I need one more digital input. So I changed this number from 4 to 5. Also, I have an output that can receive and display the integer numbers. Now let's connect the new equipment to my PLC. The next step is improving my PLC program using these addresses. This is the program which I improved it using a timer instruction. I can improve it further after the last run, but let me write the counting program part in another routine. So let's right click here and create another routine under the main program. First, let's select a name for the new routine. Here, I can select its programming language. Currently, we are using the ladder language. Finally, let's determine where the new routine should be created. Now let me open the new routine. I want to write my counting program here. In the first run, let's use the second sensor to activate an up counter. In the second run, I want to use a move instruction to copy the counter's value to the int out 0 address. In the third run, I want to use the start push button to reset the counter's value. I need to call this program from the main routine. So in the last run of the main program, let's use a jump to subroutine instruction to call the count box routine. Now let's compile the project and download it to the controller. I transferred the program to the PLC. Now let's click here to connect Factory IO to the controller. Factory IO is connected to the PLC successfully, but it has not detected this tag. Do you know why? Note that I defined this tag under the main program, not under my controller. Factory IO can only detect and connect to tags which are defined on the controller tags table, like the addresses of my digital input-output modules. So I have to delete this tag and define it again on the controller tags table. Now let me download the program to my controller. Again, let's connect Factory IO to the controller. OK, Factory IO is connected to all selected tags or addresses of the PLC successfully. Now, let's test the project. Obviously, my program is working correctly. Here I can see the number of the moved boxes. I hope you enjoyed this video. In the next video, we will continue learning RSLogix 5000 instructions with math and comparison instructions. See you in the next video.